Okay, so in this next video we'll introduce the trace of a matrix, which is another operation that we can perform on a matrix. So far we've introduced two different sort of operations that apply to certain matrices. The inverse of a matrix gives me another matrix. The transpose of a matrix gives me another matrix. The trace of a matrix actually takes a matrix in and gives us a number. And that number is quite simple, so we won't have to say very much about the trace. The trace is simply the sum of the diagonal entries. Okay, so this is something we could define for a square matrix. Technically, if you want to, you could define this for a non-square matrix, but generally this is something we're interested in for a square matrix. Okay, so the trace is just the sum of the diagonal entries. Okay, so if A looks like 3, 1, 2, 0, minus 5, 1, 1, 4, 6. The trace of A is, well, I just sum along the main diagonal. So it's 3 minus 5 plus 6, which gives me 4. If B minus 1, 0, 2, 1, 4, 0, 9, 8, 1, 2, 7, 6, minus 1, 4, 1, 2. Again, I go along the diagonal, search out those entries there, and the trace of B is going to be minus 1 plus 0 plus 7 plus 2, so I get 8. Right? So that's really it. That's all there is to the trace. It's a pretty simple thing. You might wonder why we're interested in it again. We won't see very many applications of the trace in 1410. For operators that are defined by matrices, so functions acting on vector spaces, the trace can be interesting. It will give you some sort of information about those functions. This can be especially interesting in say, kind of more advanced courses in analysis where you're studying, let's say, differential operators. You can sometimes define trace in that context. That's a much harder situation because there you're dealing with operators on infinite dimensional vector spaces, and so a trace is no longer a finite sum, and you have to be a little bit more clever to define something there. But the trace is, it is something which does play certain roles. We will see one example in the next chapter when we talk about eigenvalues and eigenvectors. We'll see that the trace does show up somewhere. Now, the trace also has certain properties. Okay, so some of the properties that the trace has is that the trace of the sum is the sum of the traces. If there's a scalar, you can pull it out. Actually, what this does tell me, this tells me that this sort of map, the trace map, which goes from the, so let's call it mn by n r. Let's use this notation here. So this is the set of n by n matrices. Okay, so it's a function that takes a matrix and gives you a real number. What these properties tell me is that the trace map is actually a linear map. Okay, it's a linear transformation. So you might kind of think about, well, if it's a linear transformation, it should be represented by a matrix. What is that matrix? Well, actually, it's not a very interesting matrix because it's, the images are, it's going to be a single, I guess, column. Column? Yeah, column. You can think about it that way, but this is maybe not so interesting. Okay, the trace also doesn't care about transpose, right? Because we know that the transpose leaves the diagonal alone, and the trace really only depends on the diagonal entries. And the other one, even though we know that A times B is not necessarily the same as B times A, the trace of A times B is equal to the trace of B times A. And so that can sometimes be useful. Okay. Now, one of the things that you can use with the trace, if we want to sort of give one example of where you might make use of the trace gives you in some sense a measure of the size of a matrix, at least this quantity here, the trace of A transpose times A. Let me show you what it looks like in the 2 by 2 case, and you can work out for yourself that this actually generalizes. So let's say that A looks like A, B, C, D. A transpose looks like A, C, B, D. We swap the B and the C. So A transpose A, C, B, D, A, B, C, D. I'm going to get, so I get A squared plus C squared. Then I get AB plus CD. I get AB plus CD, and I get B squared plus D squared. So what is the trace of A transpose A? It's the sum of the squares of the entries in my matrix, right? And so if we think about defining length of a vector, right, how do we define length of a vector? We take the sum of the squares of the entries, and then we would take the square root. So this, if we wanted to define in some sense the magnitude of a matrix, this is one way you could do it. Okay, so that's it for the trace. In the next video, we'll move on to the determinant, which is the final operation on matrices that we're going to introduce. And computationally, it's going to be the one that's sort of the most challenging. The determinant is nowhere near as simple as the trace or the transpose.